Alright, time for math. Easy solution. We're going to discuss part 2 of my related rates series. Basically, just wanted to clarify this and look further into it. Basically, here's an example that I want to go through. I found this in my calculus book and it's pretty useful. So basically, a water tank has a shape of an inverted circular cone, radius 2 meters and a height 4 meters. If water is being pumped into the tank at 2 meters cubed per minute, find the rate at which the water level is rising when the water is basically 3 meters deep. So to solve this, we have to find out what basically the water level rising rate is. And again, when we're given that the rate of the volume change, or basically how much water you're putting in. So we could start off by drawing what this is. A water tank is the shape of an inverted circular cone. So inverted is going to be upside down. So it's going to be something like this. So we'll have a cone like this. It's a circular, it just means the base or the top is a circle. So then, and then radius is 2. So let's say r is 2. Okay, and also the height is 4. So this height here is 4 meters, or basically this one right all the way down here. And if water is being pumped into the tank at 2 meters per second, let's say you're just putting water inside at a rate. Well, it's a meters cubed per minute. So basically, this is actually volume change. So this the change in volume, or derivative of volume, or dV over dt of the water inside. Here, we're changing by adding 2 meters cubed per minute. So yeah, the change in volume per time or per minute. And then find the rate of the water level rising. So here we'll give this as h as the water level. So h is the water level here. And then at this here, basically it's a cone, right? But this radius is smaller. So we'll call this r. And so at 3 meters deep. So this is, let's say, at h equals to 3 meters. What is h prime? Or dh over dt. So this is all that we were asking. Here now we're going to use similar triangles here to get a relation between r and h. But first I'll just write the equation for volume of a circular cone is just 1 over 3 pi r squared times h. Then we get to do derivative here, but if we do derivative here, we're going to have using chain rule, we're going to have derivative of h and derivative of r, but in r we're not asked to solve for it. And so here r actually the radius actually gets smaller, so it changes as well. But what we want to do is use similar triangles to basically get a relation between r and h. And we want to relate r in terms of h. So then we only have one variable, and we just get the derivative of it in terms of h. And then using similar triangles here, if we had an angle here, theta, we know that tan theta is just equal to, well, it's just similar triangle, so r over h. And on the general, the big one is the same angle, so we could do 2 over 4 numbers, opposite over adjacent. So now we have a relation between, we have this. So we just solve for r. R is just going to be equal to h over 2. Then we just plug it in here. So we're going to get v is equal to 1 over 3 pi r, which is h over 2, squared times h. And this simplifies to 1 over 3 pi h cubed, well, divided by 4. This equals to, well, pi h cubed over 12. And now we can just do derivative. We have a function of v and h. We know what v prime is, so now we're just going to do derivative. V prime is just equal to, well, using power rules, this is going to be 3 pi h squared, using chain rule h prime, but there's also a 12 here. So this is using chain rule there. And now simplify this one. This is just going to be equal to pi h squared over 4 equals h prime. And now here we could just solve for h prime. H prime is going to be equal to v prime times by 4 divided by pi h squared. And now we just plug in the values. We know that this is just 2 meters cubed per minute, and this is 3, or at h is 3. So basically now we're going to get 2 meters cubed per minute times 4 divided by pi times by 3 meters squared. This one's just going to be 9. This is 8, so we're going to have 8 over 9 pi meters cubed per minute. Now put in the calculator just to get a decimal value. We're going to 8 divided by 9. We'll just put in brackets 9 pi. 9 times pi. This one is just equal to 0.028 and go and so on. So it's equal to 0.028 meters cubed per minute, or roughly that. Just make it like this, so it's approximately that. So I'll do one more example just to clarify it. Well, actually, my mistake. The units are just meters. They cancel here as squared. Yeah, not meters cubed. My bad. So this just means that 0.028 meters, or what is it, 2 millimeters, 28 millimeters per minute is the rate that the volume, the height is going up. And then make sure you get your units. This meters cubed cancels with meters squared. This is going to be meter. So basically now let's do example 2. So example 2 states basically a man walks along a straight path at a speed of 4 feet per second, and a searchlight is located on the ground 20 feet from the path and is kept focused on the man. At what rate is the searchlight rotating when the man is 15 feet from the point closest to the searchlight? So once again, drawing a diagram will help out basically what this is trying to say. So a man walks along a straight path. Let's just draw a straight path like this. And let's say some guy, that's how he looks like. He's walking at 4 feet per second. And the searchlight is located on the ground 20 feet from the path. So let's say this is the path that he's walking. It's a straight path. So 20 feet from it is just going to be, well, just draw a perpendicular line, because that's usually how it is. So basically this perpendicular line from anywhere here, and this is going to be the searchlight. I'm going to draw it. This is draw like something like this. And that's a light. Okay, searchlight is located 20 feet from the ground, from the path, and is focused on the man. So it's going to be focusing on him. Let's draw it like that. And then let's just draw a line that is basically the distance from him to the searchlight. And it's focused. At what rate is the searchlight rotating? So basically it has to rotate because it's stuck on him the whole time when he walks. So at what rate is he rotating? Or so we want to know what theta prime is equal to what. Basically it's going to d theta over dt. This is another way of writing it. Okay, when the man is 15 feet from the point closest to the searchlight. Well, if the searchlight is here, the point closest to it on the path is just this point. We just chose this point to be where this is. So the point closest to it is this one's going to be, well, 15. So, or we'll label this as x. So this is at x equals 15. We want to know basically what rate this is. So at x equals 15. What rate is searchlight rotating on the man is 15 from the point closest is the point closest to it, and we'll call this x. And if this distance from here to here, from where he is to the point closest is x, then this rate of him changing is just equal to, well, x prime, or dx over dt. And dt is just seconds, and that's x is feet. So now, to solve this, we again need to do all this one's 20 meters. Let me just write down for that. Searchlight 20 meters from the path, so 20 meters. So to solve this, we need to set up an equation that relates theta with x, because we are given x prime. So given x prime, want theta prime. So then we need to relate the two. Relate x and theta in an equation. And to do that, well, we know trigonometry. We know tan here. Tan is just opposite of adjacent. So then tan theta is just equal to, well, x, because we don't know. We'll just do a general one first, because we can't just put 15. Because if we do derivative, it's not a constant. It changes. So basically, we need to put x there. So x over 20 meters. That's what tan theta is. So we have our equation that relates the two. So we have the equation that relates. So now we could just do the derivative using implicit differentiation. So taking the derivative on both sides, we're going to get, well, tan theta, the derivative of that is just secant squared theta. Then using chain rule, because this one changes, it's not going to be, we don't know the derivative of it, we want it. It's basically, so secant squared theta times theta prime equals to, well, x prime divided by 20. Now we just rearrange for theta prime. We're going to get theta prime is equal to x prime divided by 20 times it by, well, 1 over secant squared theta. And we know that secant squared theta, this one is just equal to, by definition, 1 over cosine squared theta. So because basically secant is 1 over cos. So then plugging that in here, we're going to get just x prime over 20, well, times 1 divided by 1 divided by cos squared is just going to be flip it over. So we're going to get cos squared theta. So now all we have to do is solve for cos squared theta. And to do that, well, we look at this triangle here, and we could just use similar triangles or just calculate the value here, because we know that the triangle looks like this. And this is at 15, so basically, let's say at x equals to 15, we're going to get, here is going to be a 15, this is 20, and we need to know what this is. Let's call this h, or hypotenuse. And given this value, this is a right angle triangle. So now using trigonometry, cosine is just adjacent of hypotenuse, so cosine theta is equal to 20 over h. But, and also you could also use similar triangles. This one is similar to, well, if we were to divide everything out here, because we know that, well, h squared is equal to 20 squared plus 15 squared, or h is equal to, well, let's say 20 squared plus 15 squared. But similar triangles there, let's say if we divide this all out by 5, we're gonna get, well, this is similar to, this is the exact same thing as having it written like this, because all we're doing is looking for ratios. Divided by 5 here is going to be a 4, divided by 5 here is going to be a 3, and then here we're going to have, well, h over, yeah, so then if we had, let's call this h2, basically over here we're going to get h2 is equal to, this is going to be 4 squared plus 9, well, yeah, 3 squared. This just equals to 16 plus 9, which equals 2 square root 25, and this equals to 5. So then we're going to get, yeah, 5. So from here, we know that this is theta, cosine theta is just going to be equal to, well, 4 over 5. And then here, if you were to times this by 5, this is going to be the same thing. So this one's actually just going to be 25, just by using similar triangles. Because this one, yeah, this one's also equal to, if you times it by 5, it's just going to be 20 over 25. And this one is h. So basically using similar triangles is easy to calculate without having put in the calculator, because I don't know what 20 squared or 15 squared is. So you could just divide this all out by 5, or a common number. So basically we got that cos theta is equal to 4 over 5. Now we just plug it in and we get our answer. So this is just going to be equal to 4 over 5 squared. So now we'll just write it down here. So we get theta is equal to x prime over 20 times by 4 over 5 squared. And then plug this all in. We know that the guy x prime is just 4 feet per second. That's how fast the guy's moving. So this is going to be 4 feet per second times by whatever this is. This is 16 over 25 times 2 times 20. 20 times 25. Simplify this further. We're going to get, this is going to be just, we'll ignore the units right now. 420, divide this by 4, divide by this 4. We're going to get 16 over 5 times 125. 25. And 5 times 25 is just 125. So our final answer, we can leave it off like this, 16 over 125. This is just feet per second. So the angle is changing at 16 over 125. Well, we put in the calculator. Here we could just put it in over here. We'll get whatever this is, 16 divided by 125. This equals 2. Well, 0.128. So that's our final answer. So then this equals 2.128. This is 0 feet per second. Well, that's all for today. Hopefully you learned. Basically, we got the rate of change of the angle as it rotates. So this kind of, so at the rate it's turning, and it's at 0.128 feet per second. And yeah, we got it just using similar triangles here, and also relating the rates of what we're given, which is x prime, using just the equation we can derive that has both of them. So we're using tan theta. Well, that's all for today. Hopefully you learn from these two examples. It's pretty useful. Everything else in calculus is basically similar to these. You got these, you'll be fine for calculus. Well, anyways, thanks for watching, and stay tuned for another math easy solution.